saving, right, or something like the constant. What is more efficient? Is it the constant primary chill water system, or the variable primary chill water system, or the constant primary and variable secondary system? Okay, if you look at the primary system, if I divide primary constant system, right, you see that the pump, there's only one pump, okay, that send water. There's only one pump that send water to the cooling coil, okay, or the cooling coil on the AHU that I showed you last week, alright, in my lab, okay, and this pump, okay, is a constant flow because the chill water flow through the chiller, okay, in the old days the chiller doesn't have that technology, so the chillers are on constant flow. So you will see this type of arrangement in building, okay, because the pump will flow at a constant speed, regardless of the flow, okay. So therefore, you doesn't take advantage of the VSD drive, alright, of energy saving, okay. So the balance of water will then flow in here, alright. So the flow will be constant all the time. So your consumption of energy will be high, okay, because your pump does not operate on variable speed. Is that clear? Yeah. Okay. Then we look at the second one. Okay. So the second one, so their building they designed like this. Okay, especially older building. Alright, they are designed with this configuration. There's also some building that are designed like this. Okay, so the pump. Okay, one pump, two pump, three pump. These pumps are on variable flow. Okay, they take advantage of the VSD. Alright, so they are on the primary. Side. This pump, this chill water pump, okay, is on the primary side. That means they supply water through a common flow. Alright, okay, through a common flow under here. This is a common header. When they supply water to a common pipe, they call this pipe the common header. Alright, then this pipe, then all the water combined will then go through here. So there's some advantage of taking the chill water flow. But this pump will have to pump water through the pump as well as the secondary loop. Alright, so this pump is actually sized on the most critical path. Alright, so to ensure that there's enough pressure to meet the most critical load in the circuit. Okay, so that there's flow in the most critical path AHU. You understand what is the critical path? Eunice, sorry, can we make recording? Can I ensure that it's already a record? Sorry. My apology again. Sorry. Please. It's important for us. Yeah. So many things to do when you start the class. Do the. Okay, I repeat again. The first one, since the recording just started. The first one is the pump is on constant flow. Alright, through the chiller. Okay, so this pump also is sized based on the critical path load. Okay, so what does it mean by critical path load? It means this. So I have a pump. This is my chiller. Okay, so the pump is pumping to the chiller. Okay. Then all the way to the loop, AHU. AHU water go to AHU. Now there are a lot of AHU. Right. So this pump, that pump the chill water, it must meet the critical path. Oh sorry, this is the wrong side. Okay, must meet the critical path. Means that the path has the highest resistance. Okay, so this pump is actually quite a big pump. Alright, to meet all the loop. Okay, so that to ensure that water can reach the last loop. Okay, with the most critical path. Alright. Because the pipe, maybe the HU has very long pipe, is the furthest away, and there are many restrictions because of the number of band, okay, in the pipe, okay, and so on and so forth. Alright. So this pump will be sized quite big, okay, and when it's sized big, it's not an issue, but it's also constant speed, okay, and doesn't take advantage of variable speed drive. Alright. So this pump will consume a lot of energy, okay. Alright. Any question on the first arrangement? Any question? No, good, Okay, do the second one. The second one is like the first one, okay, but except that they are supplying chill water now. They are supplying chill water now to a common header. Alright, this is a common header. Okay, so the pump are supplying water to a common header, and all this water will be gathered together and pumped to whatever pump that is running. Alright, so this pump itself can run on variable speed. Okay, so variable speed. Alright, and again, this pump is sized to meet the critical load path. But the only thing is that when the load is low, this one can run on variable speed. So there are some energy saving. Right? But this pump is again very big size because it has to meet the critical path. The critical path of the next one here. Okay, you can see that this pump is now smaller. Okay, it's actually draw smaller size compared to this one. Okay, so this pump itself actually responsible for the chill water that flow through the chiller only. Alright, through the chiller only. Okay, and this one can be constant speed. Alright, constant speed, because the flow through the chiller is still constant speed. Okay, and they supply to a common header. Now the chiller always supply constant flow, but the load are on variable flow. Right, so the secondary pump will be responsible for pumping the water through the secondary load. So these pumps are sized based on the resistance of the secondary flow. Okay, so this pump will have energy saving, right, and their size are smaller compared to this case. Okay, this case where the pump is just one pump, there's no secondary flow. Alright, so what is the advantage of this? Is that advantage of this, you can actually control this pump, okay, to meet the load in the secondary, alright, without affecting the flow through the chiller. Alright, so there will be energy saving here. Okay, if you ask me, right, your question is to ask me, right, which one is the best, okay? All kind of designs also have, alright, it depends on the consultant, what the consultant come up with, the design, okay, and which one is efficient or not, right? Of course, the first one is not very efficient because it's just a constant flow, alright? The second one will have energy saving, and the third one will have energy saving. But the problem with the third one is that the installation cost may be high, because you need to size for one set of primary chill water pump and another set of secondary chill water pump, and you must have space in your lab. Okay, you must have space in your compound. Alright, sometimes architect give very small room to M&E consultant. Okay, so during the construction stage, there might not be enough space to place all these pumps. Alright. If the on the second one, right, I think if the building load is not very big, alright, it's the second one. If the building load is not very big, I think the second one will be quite good. But if the building load is very big, right, but very big building with many stories, right, then I think the last one will be better, because if you have downtown 50, 60 story building, right, okay, then I think you might want to have a separate secondary pump just to take care of the pumping, okay, towards the AHU, alright, to the upper floor. Okay, yeah. Okay. I hope I answered some question. Lee, is it okay? Yeah. I have removed your assignment already, alright. Okay, and once again, I prefer communication on the MS Team because my email, every day I open my email, it's like that a lot. Okay, and a lot of them, most of my work are admin work. So if your student work come in, it will be like this. It's a lot, yeah. There are a lot of admin work I'm doing. Lecturers in me don't just teach. Yeah, we do a lot of things. Okay, my admin work is, okay, this is my job, right? My admin work is 3/4 of what I'm doing. I'm only doing 1/4 teaching. Alright, and and it's very xiong. Yeah, I have to write papers, I do industrial consultation. Yeah, and immediately after this course finish, right, I will have to go. I have been keeping my intern student at bay. I couldn't visit the supervisor for the assessment, cannot make appointment because I'm teaching actually SGUP throughout the day. So it's very hard for me to go in the morning, rush back to teach. So that we have a lot of work, including myself and Leon. Leon used to be a lecturer, but now he's posted out. Yeah, but he will come back again. And most of us, teaching work is actually a small portion. Our admin work is a lot, okay? It's a lot work, yeah. Just to write a paper for our standard approval is take me months, yeah, a few months to do it, yeah. Okay, so I have a lot of admin work. So I appreciate students got anything, consider you student, though you're young. My students respond to me on MS Teams so that I can reply very fast. Because another reason is that my email system, I cannot just log in like that. I got to do VPN to got to my email. Alright. So sometimes when I'm doing work on my computer, I don't VPN. When I don't VPN, I cannot read email. Alright. Because VPN slow down my network. Like now I'm teaching. I'm teaching now. I turn off my VPN because I cannot read my email. Okay, but I can still read MS Teams. MS Teams is no problem because it doesn't require me to do VPN. So I appreciate it. That's why sometimes students send me an email. I can't read until next day when I do VPN. But if you do MS Teams with me, I can read almost immediately. So I can also respond to you faster lah. Okay, yeah. Thank you so much. Yeah. Okay, now we continue with our heat balance. Then later on, I come back to the practical. Wow. I asked my colleague I said, where are the lab sheet? How come none of them submit the lab sheet? They said they all take home the lab sheet. I said, huh? Okay, by the way, you must submit your lab sheet. Okay, if not, I won't be asking you to stay back and do your lab sheet. Okay, so for those who didn't attend, I come back to you later. Alright, I created a portal for you to submit. Okay, as I said, I'm trying to gather as much work you do to support your assessment work, alright? So if you do your lab sheet and you keep yourself, I cannot give you assessment work. Okay, understand? Okay, if not in replace of the practical, I may give you another project to do, yeah, but it's the chance like that. Okay, right, okay, hope you understand, Okay, right, let's continue with our heat balance. Okay, heat balance is, okay, let's talk about heat balance. Okay, I haven't got the chance to go to heat balance, okay, but then we have to do our lab, yeah. So heat balance is referring to the chiller only, right? It's the chiller performance, okay. Somebody also asked me, does the tree configuration have something to do with the heat balance? No, the heat balance is pertaining to the chiller only, alright. It's the chiller ability to reject heat, okay. So the chiller itself has the evaporator, the compressor, the condenser, and also the throttling valve. Alright. So if you haven't learned pH diagram, this is what the pH diagram look like. Okay. So the law of mass, or the law of mass, or the law of heat, or the law of energy. Okay. Can somebody tell me what's the conservation law of mass or energy or whatever? What's the conversation? Energy cannot be created or destroyed, right? But can change from one form to another. Yeah, right. Okay, very good. Okay, so that means if the chiller take up so much heat, right? Okay, if the chiller evaporator suck in all the heat from the building, right? It must be able to reject by the compressor side, right? Okay, so if I have a chiller here like this is the condenser side. This is the evaporator side. Okay, so the evaporator take in the chill water, alright, then the condenser with color, okay, bring it to the cooling tower, alright. Okay. Okay. So when the water goes to evaporator, removed by the refrigeration, right? The heat that they absorb, okay, is then passed to the evaporator side. So whatever go in must be able to go whatever go out, right? Correct or not? Others. Okay. Supposed to be an arrow. Drop my stick first. Sorry. Whatever hit, this is in, this is up. Okay, whatever energy is absorbed by the evaporator, okay, must be equals to the heat that can be rejected by. Then I can say that this chiller is 100% efficient. Alright, but we don't forget there's another heat, there's a compressor inside. So there's a compressor, the motor inside that when it's running, it produces heat. Okay, so there's a compressor inside. So that means the heat plus the compressor heat, the W input, which is called the compressor heat W input, okay, must be equals to the heat. The condenser set must be able to remove the heat from the compressor, this compressor, okay, this compressor here. The heat that is rejected to the cooling tower must be the heat that is taken from all the building plus the heat that is produced by the compressor. Correct? Then we can say 100%. Correct? Then whatever come in minus whatever go out. That is perfect. Correct? See lah, 1,000. This month you spend $1,000. Correct? Know that, right? You know that, right? You know that is good. Okay? But okay, so this what is trying to say that to test your chiller performance, okay, just a chiller site, any chiller, okay, the heat that can absorb by the chiller plus the heat produced by the compressor inside too, okay, because when it works right, it generates a heat, must be totally removed by the condenser site, okay, and the heat balance must be 0. But in real life, nothing is perfect, right? Nothing is ideal. So they say, okay, since we don't expect ideal, because if BCA said that the heat balance must be die 0, every building will fail their heat balance test. Alright? Because there's no perfect system in the world. Alright? So they say, okay, then we allow 5 plus minus 5%. So that's why Mr. Ang that day let ask me, hey, you mean got minus, is it correct or not? It's correct. Remember I told you, yeah, he asked me, hey, there's a minus value, is it correct? I said, yes, it's correct. Because sometimes, if it's minus means what? If it's plus means that, if you look at the equation, this plus this minus this equals 100, okay, will be positive. But if this minus this become negative, means that the condenser is rejecting more heat than it can receive. Okay, maybe due to some error problem. Alright. So what I'm trying to say here now is, okay, whatever go in must be equals to whatever go out. So he said that, but the heat balance, okay, operate under the normal operating hour. That means for office building it is 9 to 6 as specified. If you have 80% of the data, the heat balance must be between plus minus 5%, okay, over the 1 week. Alright. So what the energy auditor do, okay? What they do is that they will, before I come to this, what the energy auditor do is that they will set up their sensors. Okay, yesterday I showed you in the lab, last Friday I showed you in the lab. The heat, the reading, right? Take the chill water temperature, condenser water temperature, and the flow rate. Okay, they take the condenser water temperature, condenser water supply temperature, condenser water return, and the flow rate, and the power. Alright, they calculate the heat gain. Okay, the heat gain is the cooling load lah. Okay, CP delta T. Okay, CP will be 4.19 times Q will be the flow rate here minus multiplied by the temperature difference. You get this one. Okay, this reading is taken from 4.19 Q 9.75 times the difference between these two temperatures. And so these are all calculated. Can you see that the heat balance, the plus minus, plus minus, plus minus, plus minus. Okay, so they take it for 1 week. The data that the energy auditor do is that they have to take this reading for 1 week. Okay, just now this one says take for 1 week, over 1 week. Alright, so they put the data logger there, okay, and record all the reading, all this reading over every single minute. You can see 15:01, 15:02, every single minute, 9 to 6 p.m. for office building, 5 days a week, okay, 5 days, Monday to Friday, alright, and then compute the heat balance. 80% of this heat balance must be within plus minus 5%. Okay, so you can see this calculation here. The percentage of the heat balance within plus minus 5% is 82%. So that means this building passes the heat balance test. Alright, so you can put the heat balance test onto a graph. Okay, the plus minus 5% is last row into the graph. Those that have the spikes, alright, maybe on that day, the sensor reading not so accurate. So sometimes the sensor reading not so accurate, so they will produce 1-2 result that is not plus minus 5%. Okay, so this is what meant by the heat balance test. You understand why they do heat balance test? You understand why they do heat balance test? It's a measure of the chiller efficiency. Alright, okay, because under the law of conservation of energy, whatever create or destroy, okay, whatever comes in to that space, what comes in must equals to what go out. That's called the balance of conservation, nature, and things like that. It's the same. Okay, right. Okay, so that's what we have to do under the energy audit, and they must submit this energy audit to BCA. Okay, this report, the calculation, yes, but the graph that shows this data, the energy auditor must submit to the BCA. Right. So you can see that under the heat balance, okay, number of count more than 5, 0. Number of count less than 5, 4. The data count within plus minus error is 18. Alright, so this is 82%. Okay, 80% does not meet. Right. Any questions so far on the heat balance test? Okay, yeah. So you can see under the report, give me a minute, I bring out the file for you. The mark report. Okay, sorry about that. I'm trying to bring out the Excel file as well. Okay. Okay, so remember, let me share screen again. Okay, remember the